Right. How are things going?
Good.
Good.
Just waited for a couple more minutes. I guess for the first couple of lectures, people logged in a little early. Now that everything's going somewhat smoothly, I guess people are trying to get there exactly on time, a little bit late. Okay, now we're up to 20. How's the homework going so far? Anyone? I know that there have been some discussions on Piazza. But other than that, it seems to be going okay. Since no one's thinking, I assume it's going okay. You guys can hear me, right?
Yeah.
Yes.
Yeah.
All right.
I just haven't started the homework yet.
Let's get started with the lecture, and let's, as is my usual practice, we'll quickly go over the material from the previous lecture just to give us a context for today's lecture. So we started talking about unconstrained optimization in lecture 3, and we looked at necessary conditions, right, for optimality. And the necessary conditions we derived were kind of generalizations of something you would have seen in calculus. That is that we showed that if f is continuously differentiable, of course, and x star is a local extremum, either local maximum or minimum, then the gradient must be 0. Of course, the points at which the gradient is 0, which are called stationary points, don't necessarily correspond to extrema. So they could be things like saddle points or inflection points. So we discussed that. Then we also talked about second order necessary conditions for which we require the function to be twice continuously differentiable. And we wrote the second order conditions in terms of the Hessian. And basically, if x star is a local minimum, not only the gradient has to be 0, but for a minimum, the Hessian has to be positive semi-definite. Right? And again, we established this thing using Taylor series expansions and mean value theorem kind of arguments for functions whose domain is one-dimensional, or the domain is the real line, and things that you learn in calculus. Right? And then we looked at sufficient conditions, and sufficient condition is if the gradient is 0 and the Hessian is positive definite, then x star is a local minimum. If it's negative definite, that's a local maximum. But if it's equal to 0, we already saw that it could be an inflection point. So you can't include 0 in the sufficient condition for optimality for the Hessian. Okay. All right. Anything else we talked about? Then we did an example how we can use these necessary and sufficient conditions to find solutions, and we went through an example. And you'll see that again, it's only in simple examples that you can follow such procedures to find optimal solutions. And in general, for most functions that you'll encounter in practice, especially in high dimensions, you'll have to resort to iterative methods, which we'll talk about next week. Okay. All right. So then we talked about, so then we started talking about convex sets and convex functions, and then we'll see why convexity will play an important role in optimization. Okay, and we'll touch upon that in today's lecture. Okay, so this is convex functions. We looked at some properties of convex functions and things like when you sum convex functions, you get a convex function. If you take the max set of convex functions, you get a convex function. Okay, so any burning questions about last lecture? If not, we can go to today's lecture. Okay, let's see where we are here. Today's, sorry, there it is. Okay, so first let's see what convexity tells us about minima and maxima. Okay, so let's say we have a convex set S, and f is a convex function on S. Then if x star is a local minimum, if it's a convex function, again, think of the picture of your quadratic or whatever that you learned in your calculus class. If x star is a local minimum, then it's also going to be a global minimum. So that's one nice thing about a convex function. Okay. It doesn't have to be unique, because there could be multiple local minima, but they're all going to equal each other. They're going to be all be global minima as well for a convex function. Now, f is strictly convex function. It's a strictly convex function. Then the minimum is unique. Okay, and if you replace min by a max, so if you look at local max, then that holds true for concave functions. Okay. So let's see. So why is this true? This is actually quite easy to show. So suppose x star is a local minimum, but it's not a global minimum, right? Let's see what happens in that case. We'll arrive at a contradiction. Okay. So what does it mean that it's not a global minimum? Then there exists a y belonging to the set S, such that fy is strictly less than f of x star, because x star is not the global minimum. It's only a local minimum, right? Okay, so that's true. But now let's look at the point alpha y plus 1 minus alpha x star. From the convexity of S, since y belongs to S and x star belongs to S, this has to belong to S. Okay? So now we exploit the convexity of the function f on S. Then we get the inequality that this is less than alpha times f of y plus 1 minus alpha f of x star. This is true for all alpha and 0, 1 by convexity of f. But this, by our assumption that x star is a local min but not a global min, we have the fy is less than f of x star. So the right hand side of this is strictly less than alpha f of x star plus 1 minus alpha f of x star for all alpha and 0, 1. So what this is saying is that the left-hand side, by the way, I can rewrite this alpha y plus 1 minus alpha x star. I'll just take the x star with a 1 and put it down here, and take the alpha and multiply it by y minus x star. Okay, so I get this. This is the same as this. So basically, this thing by above inequality, because this and this are the same, alpha 1 minus alpha just become 1. So you just get that this is less than f of x star for all alpha belonging to 0, 1. Okay. So this is true, but this is true not just for alpha in the closed interval 0, 1. This is also true in the open interval 0, 1, because it's true in the entire closed interval. So I can make this inequality hold for, so this inequality is true for alpha strictly positive, however small. So if this is true, then basically I have something, I have something, I can make close to X star, and the value is actually less than X star. No matter how close I get to X star, the value at that point is strictly less than f of X star. But that contradicts the fact that X star is a local minimum. That cannot happen if X star is a local minimum. Because if X star is a local minimum, I should be able to find a ball, okay, around X star for which the value of the function X star, f of X star, is actually smaller than or equal to the value of the function everywhere in the ball. But here I'm finding a point now that I cannot construct such a ball, is what I'm saying, okay, because of this inequality, right? And so this means that X star cannot be a local minimum. And that's a contradiction. And so the hypothesis that X star is a local minimum but not a global minimum is false. So if X star is a local minimum, it has to be also a global minimum. Okay, is that argument clear? All right. So now let's look at part 2. This says that if f is strictly convex, then the minimum has to be unique. Okay. So typically when you try to prove uniqueness, all you have to do is assume that it's not unique and then show that it leads to a contradiction. So let's suppose y is another minimum where y is different from X star. Okay, since it's a minimum, then f of y must equal f of X star, right? Because they're both minima, global minima. By the way, when you say minimum, okay, without the local in front of it, we mean global minimum, okay? All right. So now let's look at the convex combination half of X star plus half of y. By the strict convexity, oh, by the way, this, of course, we are going to assume that y, this is another minimum belonging to S, of course. So this quantity, since it's a convex combination of X star and y both belong to S, so this belongs to S. Right? And so this is less than half f of X star plus half f of y. Why is this true? Yeah? Anyone? Why is this strict inequality true? Let's go back up. We are assuming that f here is strictly convex. Okay, and under that condition, we want to show that the minimum is unique. Okay, so since f is strictly convex, this is going to be a strict inequality for any alpha not equal to 0 or 1, and X star not equal to y. That's what we have assumed here. So this is going to be a strict inequality, a strict convexity. Okay, but we now have that f of y is the same as f of X star. So this is just f of X star on the right-hand side. So what we have now shown is that f of X star is bigger than f of half X star plus half of y, which is something different from X star. So since that holds, X star cannot be a minimum, right? Because basically, we already said this, X star is not a minimum because I found something else that has a smaller value of F. And this is a contradiction. Okay, so the minimum has to be unique if F is strictly convex. And again, these are all intuitive results. Okay? And the third one says that you can replace, if you replace min by max, you can replace min by max for concave F. And that's obvious, basically. You replace the less than equal to or less than in all of the steps above by greater than equal to and greater than. Okay, and that goes through. Right. So the nice thing about convex functions is that all local minima are global minima, and if it's strictly convex, there's only one minimum. Okay, and we'll again exploit these properties when we look at gradient descent methods or iterative methods for optimization. All right. So now let's look at some ways to characterize convexity using using derivatives. Now, again, this is something you learned in your calculus course for functions on the real line, and so these are kind of generalizations of those ideas that you already learned. Okay. So the first result says that if F is convex on S, then Fy is, and I should have mentioned here that X and Y both belong to S, I guess. Maybe I should add that thing just to be completely technical. Yeah. So the X and Y belong to S. So if X and Y belong to S, then F of Y is bigger than equal to F of X plus the gradient at X times Y minus X. Okay. And we'll actually talk about what this inequality means in just a minute. Okay, but let's prove it first. So we'll prove the necessary part first, or the forward implication first. So to prove the forward implication, let's look at F of X plus alpha Y minus X. So this we already saw in the previous proof was equal to the convex combination F is 1 minus alpha X plus alpha Y. It's the same thing, you just rewrite it. And the convexity of F, we are assuming the convexity of F here, and then trying to show this. Okay. So from the convexity of F, so this is less than or equal to 1 minus alpha F of X plus alpha F of Y. Okay. All right. So now I'm going to move some terms around. So I'll take this F of X term from here and subtract it from the left hand side. Okay, so that's this part. Then I'm left with alpha F of Y minus alpha F of X. So I'll divide by alpha on both sides. And so what gets left on the right hand side is F of Y minus F of X. And we're almost done now, because if you take the limit as alpha goes to 0, so we know what this quantity is. In fact, we saw this thing in the last lecture. So if you see the numerator of this quantity, this is like my g of alpha that I defined. Okay, and if I take the divide by alpha and take the limit as alpha goes to 0, I get the derivative of g of alpha, which is defined to be the difference between these two functions. And we saw in the last class that the derivative g prime of alpha is the gradient of f at x transpose y minus x. Okay, so if we take the limit as alpha goes to 0, we get that on the left-hand side we get gradient of f of x transpose y minus x, and on the right-hand side you get f of y minus f of x. And that's exactly what we want to prove here. Okay. Any questions about that? Does anyone need to be reminded about why this is equal to this as alpha goes to 0? Okay. All right. So now let's prove the sufficiency part, the left arrow. So to prove it's sufficient, we need to start with the assumption, and the assumption is this, right? This thing here. We start with this assumption and establish that f has to be convex. Okay, so let's see how we exploit this. So let x and y belong to S, and let z equal this. So z, which is also belongs to S, right? So z, which is the convex combination, will belong to S. I should probably add that x, y belong to S. Then this belongs to S. Okay, so now what I'm going to do is apply that inequality to f of z. So if I look at f of z and add to it grad f of z transpose times x minus z, this must be less than or equal to f of x by the assumption on the right hand side, right? So what I've done here is I have f of x, okay, here, and f of z, this x are replaced by z, and then this is z, and the y is x and z is x. So that's how I get that inequality. All right, and now again, because the inequality holds for any xy belonging to S, it should hold for x and z. Okay? So now I'll do the same thing now, but use z to approximate y instead, f of z to approximate f of y. So. And so this has to be less than f of y. Okay, now what I do is multiply this by alpha and multiply this by 1 minus alpha. Okay, and add the two inequalities. So if I multiply by alpha and 1 minus alpha and add, then the first term becomes just f of z, and the second term will be f of z transpose times alpha times x minus z and 1 minus alpha y minus z. Okay, but if you add these up, what do you get? Because z is alpha x plus 1 minus alpha y. If you add up all these terms, it's easy to see that this is equal to 0. Okay, so this whole term goes away. What do I have on the right-hand side? On the right-hand side, I have, since I'm multiplying the first inequality by alpha, I have alpha f of x plus 1 minus alpha f of y. So what I've just shown is that f of z, which is the same as f of x alpha plus 1 minus alpha y, is less than alpha f of x plus 1 minus alpha f of y for this holds for any alpha belonging to 0, 1. So that means that f is convex. Okay, so we basically proved both sides of this implication, right? Now it's easy to show that if the inequality is strict, then you have strict convexity and vice versa. Okay, because all the steps go through except the inequality will be strict, and alpha in that case should be strictly between 0 and 1 in the proofs, but nothing will change really significantly. All right, any questions about this result?
So for the term that equal to 0, why is that?
Oh, just expand it out and exploit the fact that z is equal to alpha x plus 1 minus alpha y. You see that, so there's a 1 minus alpha y here, alpha x here, and then z alpha 1 minus alpha z will produce a minus z, and they'll just cancel out.
Okay, thank you.
Right? Okay. So now let's actually, before we go to the second order result, a second order characterization, let's actually briefly review Taylor's expansion, Taylor's theorem. So there's the Taylor's approximation and there's Taylor's theorem that you studied in your calculus class. This is for functions on the real line. So Taylor's theorem allows you to expand a function in terms of its derivatives, right? So this f sup I here is the ith derivative. Of f, with the zero derivative being the function itself. Okay. And what Taylor's theorem, which is like a generalization of the mean value theorem, says that f of y has this exact expansion in terms of the first n plus 1 derivatives. And that's what's given on the right-hand side. So you have this polynomial expansion in terms of y minus x to the I, multiplied by the derivatives. And then you have the last term. In the last term, what you do is you put not the derivative at x, because you're trying to, again, approximate f of y in terms of f of x and its derivatives, right? So, but here the last term, to get a mean value version and an exact equation here, you need to make z not equal to x, but z is some point between x and y, right? On the line between x and y, on the interval between x and y. So that can also be alternatively written using our convex combination idea. So a point between x and y is actually, can be written as oh, why am I not able to write? Okay. Oh boy. Okay, let's see. My pen is not responding. Okay, maybe. Oh boy, this is not good. I'll try re-syncing my pen. Not, I do have another pen, so let's hope this works though. Oh, come on. All right, okay. Sorry, never had this problem before. Pen won't respond. It does other things, but it can't write for some reason. All right, if you have any questions, ask them now. Aha. This guy is not responding either. Oh, I don't have restart. So I'm able to choose other things except for pen. That's bizarre. Never had that problem before. Anyone had this problem? That's bizarre. The highlighter and pen don't work. Okay. This is not good.
Maybe try restarting the app.
Restarting the app. Okay, and I'll have to go offline with my. Yeah. Oh, yeah. Okay. I may not need to, right? So I mean, I just need to close down the app and start over. Okay. Okay, let's see. That works. Okay. There we go. Thanks. All right. You must be a computer scientist. Huh? That used to be the way things worked with the old machines. You had to always restart them to make things happen. Okay, so is a z equal to alpha x plus 1 minus alpha y. So saying that z is between x and y is the same as saying z is equal to alpha x plus 1 minus alpha y for some alpha belonging to 0, 1. Okay? Everyone see that? Okay. So a special case with n equal to 0 gives us what's called the mean value theorem, right? So the mean value theorem says that f of y is f of x plus f prime of z times y minus x, right? And this is what we exploited in the last class, right? Now you could actually also write this as an approximation. In the approximation, we don't have to use the derivative at some point in between. We can just use x itself, okay? And then, but of course, you're left with an error term, right, in your approximation. So you all know this. So that's, and the error term is little o of y minus x to the power n for an nth order expansion. Now there's a multivariate generalization of this. So let's do the first order generalization. And again, this can be proved just using the result for functions on the real line. And we saw how we do that, at least in special cases in the last lecture, right? So the first order generalization says that fy, here now x and y are n-dimensional vectors. So the function is going from Rn to R. And fy is fx plus, now with the derivative is replaced by the gradient, right? So gradient of fz transpose y minus x, right? Okay, so, and this is for z equal to alpha x. So z is between x and y is the same as saying z is alpha x plus 1 minus alpha y for some alpha belonging to 0, 1. And of course, the approximation says that this is true with the gradient not at some z between x and y, but actually at x itself, plus little o over y minus x. Okay. So if you look at what we showed on the previous page, we said that if f is convex, then f of y is greater than or equal to f of x plus the gradient at x times y minus x. And if you look at the Taylor series approximation, the Taylor series approximation, that's what exactly is sitting is on the right-hand side here. So the first order characterization that we just proved says that f is convex if and only if Taylor's approximation underestimates the function. So basically, if you take a convex function, Taylor's approximation underestimates it. So Taylor's approximation underestimates, because the Taylor's approximation gives you a smaller value than the actual value of the function at y for a convex function, and the opposite for a concave function. And you already know this from just looking at a picture of a convex function, right? This is a picture of a convex function, and say I look at the value at x, and I approximate the value at y using Taylor's approximation, that is basically going along the gradient. And you'll see that the value at y for the Taylor approximation is less than the value of the actual function, so for a convex function. And the opposite would be true for a concave function. Any questions? Yeah. Now let's see what happens with the second order expansion. Second order expansion is very similar to what you saw in calculus, except for the second derivative, we'll replace it by the Hessian. Okay, and instead of y minus x squared, you'll have y minus x transpose before and y minus x on the right hand side like that. So you get a quadratic form, okay, in y minus x. And again, this is the exact version of the Taylor's theorem, where z is a convex combination of x and y for some alpha belonging to 0, 1. And the approximation holds with now little o y minus x norm squared. Okay. So let's use this to do a second order characterization of convex function. So here what we're going to show is only the implication going one way, and then I'll tell you what happens. There's some subtleties when you want to go the other way. So here we'll say that if you observe for a function that the Hessian is, so f is twice continuously differentiable, and if the Hessian of the function is positive semi-definite for all x in that set S, right, then f is convex in that set S. Okay, and if it's positive definite, so the inequality is strict, then f is strictly convex in S. Okay, and of course for concave functions you go the other way. That should be that.
Sorry.
No, that's correct. I wrote that correctly. So I thought I'd made a typo right over there. That's correct. Okay. Yeah, greater than becomes less than, greater than equal to becomes less than. Okay. Now, how do you prove this? Is actually very straightforward. Suppose the Hessian is positive semi-definite. Actually, I should put a little curlies here using my notation. For all x belonging to S. Then let's take any y belonging to S and define z equals alpha x plus 1 minus alpha y. Of course, this also belongs to S, and that implies that the Hessian of f at z is also positive semi-definite. So all we now do is plug this into our equation star, or maybe I should make it a little smaller so you can see star. So that's the equation star up there for the second order version of the Taylor's theorem. Let's use this. So you see that now we have the f of z here term in star. So if you plug this fact in here, you conclude that this term is non-negative. So that means if that's non-negative, that says that f of y is bigger than or equal to this. Okay, as simple as that. So if f of y is bigger than f of x plus the gradient of x transpose y minus x, but that was the first order necessary and sufficient condition for convexity. So this implies by our previous result first order okay, so we're done. Okay, any questions? Okay, so there's a reason why I didn't make this a necessary and sufficient condition. So there's a reason why I didn't put the implication going the other way here. Okay, and we'll see that we can actually prove this implication, but we have to put some constraints on the set S to be able to prove it. Okay, and this second one, of course, this is not going to hold. F is strictly convex does not imply that the Hessian, that should be the Hessian, by the way, not gradient, Hessian. Hessian is positive semi-definite. Okay, so that will be establish that on the next page. But before we do that, let's take a short break for a couple of minutes so I can go refresh my tea. And then we'll get started at 11:43. Any questions? Okay. No burning questions? Good. So a couple of minutes, I'll be right back. All right. Nice fresh cup of tea. Okay, so yeah, so let's actually talk about, you guys are still there, right? Okay, all right. So let's talk about going the other way. Turns out that you need a condition to be able, at least to be able to prove going the other way for positive semi-definite matrices easily. Although there are ways to slightly generalize this result, and you can look at the textbook for the details on that. Okay, so here what we're going to assume is that the set, all we have to assume to go the other way is assume that the set is an open set, and you'll see where we exploit the openness in just a minute. Okay, so it's not a serious assumption. Okay, so suppose f is twice continuously differentiable and convex over an open set S. Then you can show that the Hessian has to be positive semi-definite for all x belonging to S. So we prove this by contradiction. That seems to be a popular way to prove a lot of these results. So suppose the Hessian is not positive definite for all points in S. So then there exists some y in S for which I don't satisfy the positive definite condition. So that means there exists a y in S and u belonging to Rn such that my positive definite condition is not satisfied, a PSD condition is not satisfied, which means that U transpose times the Hessian of F at Y times U, rather than being bigger than or equal to 0, is strictly less than 0. So this must happen. Now we exploit both the continuity of the Hessian as well as the fact that S is an open set. So how I'm going to exploit is that I'm going to make the norm of U, this vector U, and of course, if this inequality holds, I can scale down U any way I like and it'll still hold. So I'm going to make my norm small, and if I make it small enough, then y minus some alpha times U belongs to S. I can make that happen. Okay, because S is open, I can make that happen. If alpha is and I can make this happen for any alpha between 0 and 1 as long as my norm of U is small. So I can make norm of U smaller and smaller and smaller so that then I get inside that ball around Y, and that will contain an S by the openness of S. And I'm also going to make it small enough so that by continuity, if I look at U transpose F squared Y minus alpha U, this is less than 0, because I know that that condition holds at Y. It's also going to hold for Y minus alpha U for small enough norm of U because of the continuity of the Hessian. And so this holds for all, I can make this hold for all alpha belonging to 0, 1. Okay, and now you can see how I can exploit this. So we'll let x equals y minus u, okay, which implies that u equals y minus x. Okay. Then we have the following. U is y minus x, so I have y minus x transpose the Hessian of f. Now, y minus alpha u is y minus alpha y minus x. And we saw an expression like this already. Okay, and so this is true for all alpha belonging to 0, 1. But this is basically the same as alpha x plus 1 minus alpha y, which is what was called z in our Taylor expansion. So if you plug that into the Taylor expansion, second order Taylor expansion star, so what we have is that this quantity here is strictly less than 0, right? So then fy must be strictly less than this. So that's what we're going to write down here. Fy must be strictly less than fx plus gradient of fx transpose y minus x. So this means that f is not convex, right? Because the first order necessary and sufficient condition for convexity was the inequality going the other way. Which is a contradiction, because we assumed up here that f is convex over the open set S. So we must have that the Hessian is positive semi-definite for all x in S. Any questions? So one quick comment here is that if S was not open, I couldn't have done this. I couldn't have guaranteed that y minus alpha u belongs to S, because if I'm on the boundary of S, I couldn't have guaranteed that this condition held. Okay, so you can actually extend this result for closed sets S, but you have to impose other conditions on S, and I'm not going to go into those details here, but you can read the book for that. Okay, so what about the result when f is strictly convex on S? So if f is strictly convex on S, then it's not necessary that the Hessian is strictly positive definite for all x and S. Okay, and we could actually just, all you have to do is give a counterexample. Okay, now it might hold in some cases, and we'll actually see an example of that on the next page. But a very simple counterexample to this result is that, let's just take anyone want to guess what that counterexample is? A function that's strictly convex on S, but the Hessian is not positive definite for all x. Anyone? I'll give you a hint. It was one of the problems on your homework. One of the problems that you showed, one of the functions in your homework that you showed was strictly convex. Anyone? You guys didn't work out the homework? No one's speaking up, huh? You can unmute, you know. All right, so I'll draw the shape of the function. It looks like this. So what function is this that for which which is strictly convex, but the Hessian is not positive.
X to the power 4th.
Yeah, x to the power 4th. Very good. So in your homework, you showed just by the definition of convexity, or you'll be showing if you haven't done that already, this is strictly convex. Okay, but if you look at the second derivative, which is the same as the Hessian in this case, this is equal to 12x squared, which is 0 at x equals 0. So it's not it's not positive definite for all x. It's actually equal to 0 at one of the points x. Okay. So you wouldn't be able to go both ways for strictly convex functions. So you can go this way, you can go this way, but you cannot go this way. You can't go. So if it's strictly positive definite, it's strictly convex. Whereas strictly convex, the Hessian need not be strictly positive definite. But it turns out for a special case of functions, quadratic functions, that it actually goes the other way as well. And we'll see that in the next slide. Questions? Okay, let's move on. Let's look at some special cases of functions that you'll encounter in this course. The affine function, which is just a linear in x plus a constant. And if you look at the gradient for this function, it's easy to see that it's just a. You can just do that by writing the inner product as a sum and taking the derivative with respect to each component. You see that that's equal to a. And the Hessian is 0. Okay, for all x. So if the Hessian is 0, you can conclude that f is both convex and concave. This is a special case of both convex and concave function. But you cannot use the results that we have established so far to say anything about whether it's strict or not. But actually, this is not going to be strict. Okay, and so that's basically we couldn't use this kind of result to conclude that it's not strict, because just because the Hessian is 0 does not mean the f cannot be strictly convex, because we just saw an example where the Hessian is 0 and the function is actually strictly convex. So how do we establish that this function is not strictly convex? But that's actually very easy in this case. We can actually show that it's not strictly convex by contradiction. So suppose we assume that this affine function is strictly convex. Okay, and then we'll have to just show that it leads to a contradiction. So let's look at f of 0. F of 0, if I put 0 here, you just get b. So b is f of 0. But I can also write f of 0 as f of half x minus half x. So this is like taking a convex combination of x and minus x. And but if we assume strict convexity on f, this must be strictly less than f of x plus half f of minus x. But if you look at f of x and f of minus x and add them up, what do you get? Say if you put f of x and then you look at f of minus x, this term will become the negative when I put a minus x. But this term is unchanged. So this when you add them up, this term, the linear term, cancels, and all I'm left with is the constant. So this is equal to b, right? But then that's a contradiction, because this is saying that b is strictly less than b. So this cannot happen. So f cannot be strictly convex. Similarly, if you assume that it's strictly concave, you'll get that b is greater than b. That's a contradiction. So it cannot be strictly concave. Okay. So even if you can't apply the general results that we showed for necessary and sufficient conditions for convexity, you might be able to establish them in special cases. Okay, here we'll look at another special case of quadratic function. Okay, and a quadratic function has the form x transpose qx plus b transpose x plus c. And generally we put a half in front of the quadratic term just for convenience. So if you put a half up there, you can easily show that the gradient is qx plus b and the Hessian is just q. If you didn't put the half, then the Hessian would be 2 times q. Okay, so that's the only reason for scaling that by half. Now we can always, in a quadratic form, we can always assume that q is symmetric. Why is that? So this is symmetric without loss of generality. Why is that? We can always assume q is symmetric in a quadratic form.
If q is not symmetric, we can just add like two of these same functions, and so that it will be symmetric.
Yeah, exactly. So if q was not symmetric, I can make q symmetric and not change the quadratic form. Okay. Maybe we'll just do a quick example. I have a sheet here. So suppose I have that, and if suppose so in this case, say q is not symmetric. Q is not equal to q transpose. Okay, suppose. Then all I can do in this summation, I write this as xi qij tilde xj, where what I can do is make qij tilde just half of qij. So qij, suppose it's not equal to qji. Ji. Okay, equals to q tilde ji. So you basically end up getting the same quadratic, the same value for the function f at x if you replace the original matrix, which may not be symmetric, by a symmetric matrix, right? So you can always, so without loss of generality, you can assume that in a quadratic form, q is symmetric. Similar reason for why you could define positive, you only need to define positive definiteness and positive semi-definiteness for symmetric matrices, okay? Because you can boil down the condition for positive definiteness of a non-symmetric matrix, if you want to define that, to actually the positive definiteness of a corresponding symmetrized matrix. So that's true. Okay, so you can easily show that the gradient is qx plus b, and the Hessian is q. Okay, and the result here for quadratic function says that the condition for whether f is convex, strictly convex, concave, or strictly concave is completely determined by the positive definiteness or positive semi-definiteness or negative definiteness or negative semi-definiteness of q, which is the same as the Hessian. Okay, so why is this true? So q is the same as the Hessian. So, well, we can actually establish most of this from the results we have shown so far. So we have actually already established one, because the Hessian being PSD is equivalent to f being convex. Now the only thing, the issue was the oh, by the way, this is for x belonging to Rn. So Rn is both, as I said, is both open and closed. So you don't have to worry about that condition of S being open here. So that will hold as well. So you can go both ways for 1 and 3. And 2 and 4, we established the forward parts, right? So all we have to now establish is going the other way. So for 2 and 4, okay. And we're going to establish, in the special case of quadratic, we can establish this. So let's actually look at going the other way for 2. So we're saying that if F is strictly convex, then if F is strictly convex, then Q has to be positive definite. So suppose F is strictly convex and Q is not positive definite. Of course, because F strictly convex means that F is convex, then Q has to be at least positive semi-definite. But suppose it's positive semi-definite, but not positive definite. So the only way that can happen is if Q has an eigenvalue that's 0, right? Remember, Q is a symmetric matrix, so all its eigenvalues are real. So a Q must have a 0 eigenvalue. So this implies that there exists an X such that Q of X equal to 0 times X, which is 0. Now let's look at F of 0. F of 0 is, for this function, F of 0 is C, right? So let's plug in, if you plug in 0 into this expression, you get C. Okay, it's very similar to the affine result to get a contradiction. So we'll write F of 0 as F of half of X plus minus a half of minus X, right? Okay, but if we look at this, if you look at F at X and F at minus X, because because Q of X is 0, this term will disappear in F of X and F of minus X. And this term will cancel out. So when you add this, you'll just get C, right? So basically this F of 0 can also be written as equal to half F of X plus half F of minus X. Because if you look at F of X is this, but this term goes away because Qx is 0. F of minus X, also this term will go away, and you're left with the linear term. The linear terms will cancel each other, and the C term, you have a half multiplying the C, so they'll just add up to give you a C. So both this and F of 0 are equal to C in that case. But this is a contradiction. Why is that? Why is this a contradiction? What does it contradict? The statement. The
C
statement
less than
that,
C.
yeah. Go ahead.
C is strictly less than C.
No. Here, I'm not exploiting that. I'm looking at this equality here. Think about this equality. What does that say about the function f? I'm taking f at a convex combination, and it's equal to the convex combinations of the f.
The function is not strictly convex.
Not strictly convex, because for a strictly convex function, I couldn't have equality here. And that's a contradiction. Okay. So Q must be positive definite. So I've established the inequality going the other way in this special case. And of course, the strictly concave conditions done similarly with the inequality going the other way. That's all. All right. Now let's actually try and understand quadratic forms a little bit more, because you'll be seeing that a lot in this course. So suppose I have this quadratic function, okay, of x. And you can identify a quadratic function because you'll only see things like, xi squared, or the cross terms, x1, x2, and so on, and or linear terms and constant. So it's again, this is an example also to illustrate that you can always construct a Q for this matrix, for this function, so that Q is symmetric. Okay, so in particular, I can write this as 2 along the diagonals. I have 2 here, and there's no x2 squared term, so there's 0 there, and then a half for x3 squared. x1, x2, there's a 1 coefficient. I can spread that out to a half here and a half here to make it symmetric. And then the x2, x3, which is this thing here. So there'll be, I'll put a 1 here and a 1 here, and then 0 here. There's no x1, x3. Okay, and then for the linear term, I have 1, 2, 0, and then I have a constant. So this can be written, if I want to have a half in front of the quadratic term, I have to multiply everything inside the matrix by 2. So I'll have 4, 1, 0, 1, 0, 2, 0, 2, 1 for my Q. And this is the same, and this is the same. Now, let's see if this function is convex or concave or neither, right? So to do that, all we have to do is check if Q is positive semi-definite or negative semi-definite, or positive definite or negative definite. Okay, so let's look at the positive semi-definite condition. So for a matrix A to be, remember that for a matrix A to be positive semi-definite, all its principal minors must be positive, right? Or sorry, must be non-negative. So let's check, but you don't have to check all of them. If you can, to get a contradiction, it's much easier just to try and see, visually if there's something that might contradict this. So some minor that's negative. Can anyone see a minor that's negative by just looking at this matrix? A principal minor. Not just the leading ones, you have to look at all the principal minors.
First 2 rows and 2 columns.
So that one actually gives me something positive.
Oh, actually, yeah, negative. Yeah.
I want to see if I can disprove positive semi-definiteness. So actually, just look at this matrix here. Okay, you see that has a negative determinant. So if you look at this minor, just principal minor, that value of the determinant is -4, which is negative. So since I found a principal minor that's negative, this cannot be, Q is not positive semi-definite. Also, well, then you can try and see maybe if Q is negative semi-definite. To do that, you can look at negative Q and see if it's positive semi-definite. But if you look at negative Q, it's obvious that it's not going to be positive semi-definite, because just look at the leading term, -4. -4 is one of the minors, and it's negative. So this means that Q is not NSD. So it's neither positive semi-definite nor negative semi-definite. Of course, it cannot, if it's not positive semi-definite, it's not going to be positive definite. And if it's not negative semi-definite, it cannot be negative definite. So it's neither PSD nor NSD, implies that in this case, F is neither convex nor concave. Okay. So finally, one last thing about convexity and derivative conditions. If you have a convex function, all you need to do is find a point at which the gradient is 0. And if you found any point at which, if you find any point at which the gradient is 0, that point is a global minimum, and you're done. You solve the problem. Okay, why is that? It's easy because if f is convex, we know that the the function is underestimated by the Taylor expansion. So f of y is bigger than f x star plus gradient of f at x star transpose y minus x star, sorry, for all y, right? And it could be all y in Rn or all y in S. And so this is 0. So this implies that fy is bigger than f of x star for all y, which implies that x star is a global minimum. Again, this is very intuitive, right? So for convex function, all you need to do is find a point at which the gradient is 0. And you're done. Okay, so let's see how we might exploit that to find the minimum to solve an optimization problem. Okay, this is an analytical way to solve an optimization problem if f is convex. All right. And again, if f is strictly convex, you know that there is a unique solution x star. So you don't have to, I mean, you don't care if you just want to find one value, find one solution to the gradient being 0 and you're done. So let's actually look at a very simple example of this, and you'll see another example in your homework. So this is a quadratic function. I could write this as x transpose 1, this quadratic form with a symmetric q plus 2, sorry, minus, not 2 here, minus 1, 0, x, and there's no constant. So if you look at the gradient of this is 2 times the matrix. I didn't normalize it with the half in front. If I'd done that, I wouldn't have the 2 here, but let's do it this way. Okay, and that's equal to the gradient will be 2. So let's go ahead and multiply the 2 in. So 2, 1, 1, 4. So 4x1, 2x1 plus x2 minus 1, and then x1 plus 4x2. So that's the gradient. If you look at the Hessian is 2, 1, 1, 4, which is easy to see that it's positive definite. Okay, so this is a strictly convex function. Okay, so let's just solve for the gradient equal to 0, and it will be done. Once we find the solution, we know that that's the minimum. So to solve that, it's easy. It's just a set of linear equations, right? So you get from the gradient equal to 0, the first equation you get is that, and the second equation is x1 plus 4x2 equals 0, which implies that x1 is minus 4x2. Plugging that up there, you get minus 7x2 equals 1. So x2 is equal to minus 1 over 7, and x1 equals 4 over 7. X1 star. Okay, and this is the global minimum. So it's great, right? So if you have a quadratic function, okay, it's very easy to find its global minimum, right? Just have to solve a bunch of linear equations for the gradient being equal to 0. But can we do this more generally? So it turns out that except in simple examples like this, solving for the gradient equal to 0 is just as difficult as trying to solve the optimization problem to start with. So you don't get any, and you don't necessarily get something simpler, and you may not be able to use any you may not be able to explicitly solve for x like in the quadratic case, because in the quadratic case you end up with a gradient being 0, giving you a linear set of linear equations which you can easily solve. So let's actually look at a very simple example just of a function in one dimension, which is x squared plus x plus e to the x. So why is this a convex function? You can actually compute its second derivative and show that it's positive, but we can also use the results that we showed last class to conclude that this is a convex function. Anyone? X squared is convex. X is both convex and concave, but it's convex. And e to the x is convex, right? Okay, so you add those things up, you get a convex function. And in fact, if any one of the components is strictly convex, the sum is going to be strictly convex. So in this case, the sum is strictly convex. Okay, but you can also conclude this by taking the second derivative. So then, if it's a convex function, to find its minimum, all we have to do is set the gradient to 0. But so let's compute the gradient. This is 2x plus 1 plus e to the x. And we have to solve for this equal to 0. But how do you solve for this equal to 0? How do you solve for x that satisfies this? Anyone remember how you might be able to solve something like this? You can't write down an explicit answer for this, right? Can you? Boy, no one's speaking. Maybe you guys need to have more coffee or tea, I guess. Come on, guys. So you might remember some iterative methods to do this, right? Anyone? Okay, and we'll actually talk about iterative methods to solve f equals 0. Anyone know what method can be used to solve this equation? There's no closed form, but how can you find a solution? I don't know, an approximate solution numerically.
Euler's method.
Euler's method. Okay, so that's one way. Any other technique you remember from your calculus classes?
Newton's method.
Newton's method, yeah. So you could use Newton's method to find, so you need an iterative method, like Newton's method. So there's no closed form. Actually, we'll revisit Newton's method in a different context as a way to solve the optimization problem, not just to solve for gradient equal to 0. So we'll actually figure out, see how we can exploit the same idea in a different way a little bit later in the course. Okay, so basically, yes, all this convex theory is useful, but it may not be useful in finding the optimum solution. You at least can characterize and something about that if you do find a solution for the gradient equal to 0, then you know for sure that you've solved your problem. At least you can say that. So then what you can do is figure out some iterative way to solve that gradient equal to 0. Okay, and basically that's what we're going to focus on in the next few lectures. So we'll start talking about gradient descent techniques to find solutions to these optimization problems. Okay. Any questions? Last minute before we stop. All right. I will see you next week. Have a good weekend.